2.
All right, I believe we were on page 334. We were looking at some properties of logs yesterday. We were kind of exploring how addition and multiplication are linked together. And the same thing with division and subtraction. Those were 2 properties. And we had some other ones, like if we had a power, we could move it out front. If the bases matched, like in terms of the log and the exponential, they would cancel. So we're just going to explore like more examples of these today, getting used to them, okay, because eventually we're going to have to utilize them to help us solve equations. I think we still have number 10 to do, is that right? Yeah? Okay. So taking a look at number 10, at first glance, I see the square root. At second glance, I see division. So maybe we can work around those, utilize a property or 2 to help us expand that log. Is there anything you want to do first? Go to Rebecca. Okay, so we know that a square root is the same thing as a power of a half. And if we have a power on the argument, we can move that in front of the log as a coefficient. So that was one of our properties from yesterday. That one's nice because it kind of gets rid of the square root. I like it. Anything else you want to do? Any other properties to expand that log? We want to go from 1 to maybe 2 or 3. We'll see how many we can get. You see what, Emily? Yeah? And y. Oh, that's a z. Sorry. Yeah, that's okay. Yeah, so we're going to go ahead and subtract it. So we'll have log of x cubed minus log of y times z. What about the 1/2 out front, though? Where do you think that should go? Yeah? Yeah, okay, so you could think about a bracket because you're taking this 1 log and expanding it into 2. So that 1/2 would kind of still be out front. How about we go ahead and distribute the 1/2 in? You want to do that? Get rid of the brackets or the parentheses? Alright, so far so good. Any other properties you notice? Good, Marie? Alright, we can bring that 3 out front. That's another power on the argument. So it become a 3/2. Can we use a property on the second log? Yeah? Add them. Perfect. Okay, so very similar to how we broke up the initial log we had at the top and we had to use brackets because we were expanding it. We're going to have to use brackets again for this one. So the 1/2 will be out front, and when we expand the log, we'll have log of y plus log of z. Now you could leave it like that if you wanted to. We could distribute in the negative 1/2. Might not be a bad idea because eventually we might have to do that if we were going to solve this for a variable. So in the end, maybe we'll say we have 3/2 log of x minus 1/2 log of y minus 1/2 log of z. That was kind of a log question on steroids. We had a bunch of things to do there. We had to get rid of a square root, we had to get rid of a division, we got rid of multiplication, we got rid of a power of 3. We used a lot of different properties. We remember them from yesterday? Seems like we do. Okay, let's go ahead and we'll check out some more on the back. Or the next page, I guess. Okay. So in these examples, we're going to go ahead and use the inverse property oh, you can't see it, sorry. We're going to use the inverse property of exponentials and logs to simplify each of them. Now, inverses just essentially means that they cancel each other out. Like if you were to add 3 and subtract 3, those would undo each other. So there were, I think, 2 properties we went over yesterday where we noticed how certain things canceled out and we were left with either kind of a power or an argument, depending on what the case was. So if you were to take a look at number 11, can you kind of tell me what you think would cancel out from that logarithmic expression? Good, Rebecca?
The natural log and the e.
Okay, perfect. So the base of a natural log is an e. The base of the argument is an e. Natural logs and exponentials are inverses. They cancel each other out. So if these, the natural log and the e is canceling each other out, what are we essentially left with? The 3x, that's it. That was one of the properties we went over yesterday. What about 12? Do you notice anything that might be able to be canceled out? Put a slash through it. Go ahead, Marie. E and the natural log. You have e, base of e for the exponential. The log is a base of e because it's a natural log. Those cancel each other out, and it looks like we're left with the argument of x plus 2. All right, let's take a look at 13. What do you think? Go, Rebecca?
The natural log would be canceled out, and since you can rewrite it, the equation would be ln e to the 2/3.
Uh-huh.
It's more obvious like the other ones, so you just be left with the 2/3.
Good. Okay, so at first glance, a lot of students, they kind of get in, because these are kind of the easier ones to notice, they kind of get in a happy mood of just slashing things out, making things go away. But you can't really do that for this one, at least with the way it looks. Because if you were to just slash out the natural log and the e, you're left with a cube root and a power of 2. Do we see anything like that in math, like just a cube root and a power of 2? Normally there's something there, right? That it has to be raised to the power of 2. So at first glance, you might think, oh my gosh, those are going to cancel, right? But you need to be strategic and think about what's actually left. Does it make sense? So if you look at this and think the cube root and square don't make sense, maybe we can rewrite this somehow so it does. Now, so Rebecca kind of transformed the cubed root into that fraction of a third in the bottom, or a 3 in the bottom, and then the 2 would be the power on top. So now notice that what we have here matches very similar to the example we did in 11. We have the natural log of e to a power. So now these would cancel out, and we're just left with that power of 2/3, much like we were left with the power of 3x in 11. Okay, so these are semi-easy because things are going to cancel out and go away, and we like that when it happens, but you got to be strategic and aware of what's actually left. Okay, does it make sense? Let's check out 14. Before we get slash happy, okay, can we rewrite it somehow? Maybe use a property of logs? What do you think, Marie? Yeah?
Well, log is 5 times.
Say it again?
Isn't there a way we can cancel out because log is by 10?
Uh-huh. So this base of 10 should eventually cancel out the log because that log has a base of 10. It's a common log. But before we get slash happy, okay, let's make sure that we can probably rewrite this log using a property. Go ahead and ignore the 10 for a second. Just take a look at the log part. Yeah. There's a number in front of the log, so we can move it up as a power. So now the 10 and the log can cancel each other out. They have the same bases. One's an exponential, one's a log, so we're left with just the x squared. Again, if you were to get slash happy and immediately cancel out the 10 and the log, most of us would probably think, oh, we're left with a 2 and an x. So it's not 2x that we're left with, it's actually x squared. Because if there's a number in front of the log, according to our property, we know it was originally a power. Okay, so don't get slash happy. You got to think about your properties and does it make sense? All right, let's take a look at 15 because 15 and 12 are very, very similar, but yet they're like drastically different. Do you see how 12 had parentheses around the x plus 2? That means the x plus 2 was the argument. Bless you. What's the argument in 15? What's inside, or what can we essentially put in parentheses for that natural log? Is it both the x plus 2? I think they would have written it like this. What do you think the argument is of the natural log? Yeah? Just x. Okay? So this is e to the natural log, or natural log of x, and then plus 2. Okay? The plus 2 is not included in the argument like it was for 12. Okay? So if you don't see parentheses there, you're just to assume that the first maybe number or variable after the log is the argument. Okay, if there were more things there, they would group them together in parentheses. Okay, so let's think about this. If we think about our properties again, maybe not log properties because we're working with an exponential now. If you're adding two exponents together, what were you originally doing with the bases? Can you think about your exponent properties? If you were adding exponents, what were you originally doing with the bases? Yeah, you were multiplying them, okay? So we can rewrite this as e to the natural log of x times e squared. All right, so let's take a look at each one of those individually. If you look at the first exponential, e to the natural log of x, the e and the natural log will cancel, and we're just left with x. But the second exponential, e squared, is just a number, isn't it? Isn't e 2.718, right? And then if you square it, that's still a number. All right, so this actually simplifies to x times e squared. Again, some people might get slash happy and eventually think that this e and natural log would cancel out, so you're left with x plus 2. But that's not the case. If the x plus 2 were in parentheses, like it was for 12, that's what we would be left with. So there's a slight difference between the two, depending on where your argument is located. Again, don't get slash happy, think about your properties. All right, kind of similar question here for 16. Notice how we have 5 raised to the power of 2 plus log base 5. So if you're adding two exponents together, maybe we can rewrite that using an exponential property. We were originally multiplying the bases together. Let's see, 5 squared is pretty easy for us to figure out. That'd be 25. What about the second exponential? What do you think, Marie? It would just be x, right? The base of 5 for the exponential matches the base of the log, so those would cancel each other out. and we're just left with the x. So 25x in the end. Okay. Again, some people might be slash happy and think initially that the 5 and the log 5 would cancel, so you're left with 2 plus x, but that's not the case. Okay, think about your properties. All right, so we're going to try to bring all these different properties together, and we're officially going to start solving log equations. Okay, we'll eventually amp it up in the next section, but these again are kind of intro ones. So solve each of the following by rewriting each side of the equation as a single log. So that means we're going to have to utilize some properties to condense it. Then set the arguments equal to each other. If the equation has no solution, then specifically explain why. Okay, we'll get there in a second. Okay, but let's just first start off with the idea of using our properties to condense these logs. So taking a look at the number 17 on the left-hand side, notice how we have 2 logs and they have the same base. If you don't see the base, what's it considered to be? 10. Good. Okay. So let's go ahead and see if we can turn these 2 logs into 1 log. What are some properties that you notice? What do you think, Marie? The 2? Okay, so we'll move that 2 to the power on the argument. So that would be 2 squared. But maybe we can just rewrite that as 4. I like that. Okay, can we keep going? Remember, our goal is to get a single log. Okay, 1 logarithm on the left-hand side. We still have 2. You want to keep going? Yeah. You mean like turn this into log of x plus log of 9? Okay, that's a good question. Let's actually explore that for a second. So just as an example on your calculator, what if we tried log of 6 plus log of 3? We get that answer, right? So let's check if distributing the log is actually algebraically acceptable. If we were to distribute the log, that would look like log of 6 plus log of 3, right? Do we get the same exact thing? No. Okay, so here's what's tricky, and students make this mistake kind of all the time. Whenever you see parentheses, it's been kind of burnt into your brain since middle school that you can distribute whatever's out front. Is that a fair assumption? Okay, but a logarithm is not a number. You can distribute numbers into parentheses. A logarithm is some type of function or some type of operation. So unfortunately, you cannot distribute a log in. Okay, common misconception because the moment you see parentheses, your brain thinks distribution, but that's not the case for logs. So unfortunately, we can't really do anything to this right-hand side. Notice how it already has 1 log. That's okay. We're trying to get this side to have 1 log. Do you think we can use a property over here to turn 2 logs into 1? Good, Rebecca? There we go. If you're adding the same base log together, you can multiply the arguments. Okay. So we have 1 log on the left, 1 log on the right. If these logs are supposedly equal to each other, because we have that symbol in between them, where do you think we can go from there? If this left-hand side must equal this right-hand side, what should we kind of analyze next? What do you think, Maddie? There we go. Don't we already know the logs match each other? Aren't they the same log of the same base? So in your head or on your paper, you can think about just canceling those out because they're already the same. So we're just going to set the arguments equal to each other. That's what we're not sure of yet. That's where the variable is still located. Okay, so properties of logarithms are important because in order to solve this log equation, we had to condense those 2 logs down to 1 log. That way we could kind of imagine getting rid of the logs because now we have one of the same kind on each side. So let's see, solving for x, we can subtract over the x and then divide the 3. All right. Now the second or the last thing mentioned up here in the directions is if the equation has no solution, then specifically explain why. This is basically just asking us to check our answer. So on your calculator, we're going to go ahead and plug in 3 back into these logs. Okay, we're not going to kind of evaluate the whole equation. We're just going to plug in 3 into the logs that have an x in it. So for example, this first one, we'll just type in log of 3 and see if we get a number. So it looks like 3 would work for that log because we actually get some value out of that. Let's go ahead and check the other log that has an x in it. So that would be log of 3 plus 9, which would be 12. Notice how that log is able to be evaluated as well. Okay. Now if you wanted to, I know that we checked kind of both sides of the equation in the previous section. You could do that as well. But notice how whenever we plug 3 back in, we'll get an answer for a logarithm in either case. So it looks like 3 is a good solution. Okay, it works when we go ahead and plug it back in to check our work. All right, let's go ahead and check out 18. So we have 1 log on the left-hand side, and it looks like we have 2 logs on the right-hand side. We eventually want to get 1 log on the left, 1 log on the right. That way we can just look at the arguments, okay, figure out what the solution would be from those. So on the right-hand side, what are some properties you might want to use to change 2 logs into 1? Yeah. We can divide them, okay, because we are subtracting perfectly. Can we do something else first? There we go. All right, so on the right-hand side, we'll move the 2 up as a power. So that'd be the natural log of 4. And then to turn 2 logs into 1 log, let's go ahead and divide the arguments. We'll have x over 4. All right, 1 log on the left, 1 log on the right. They're exactly the same log, okay, both natural logs, both base of e. So in your head or on your paper, you can imagine just canceling those out because we already know they're the same. Let's go ahead and evaluate the arguments. Where do you want to go from there? Yeah. Multiply the 4 over, good. Let's see, maybe I can subtract the 8x over, so that'd be negative 7x, and then divide by negative 7, so that would end up being a positive 12 over 7. All right, let's check that answer. So in our calculator, we're going to plug in 12 over 7 in for the x's, and we're going to check those logarithms, see if we actually have a value that's able to be calculated. So if we were to check the first one, we'll have natural log, and we need 2 times 12 divided by 7, and then we need to subtract 3. Looks like we get a value. Okay, so this x solution is working for this log. Let's check out the next one. We just need natural log of 12 divided by 7. And looks like we get a value for that one. Okay, so the x solution we found is able to be substituted back in to get some type of value. So it looks like that's a good solution that we found. All right, let's try the next one. Looks like we have 2 logs on the left, 1 log on the right. All the logs have a base of 3, so that's a good thing to notice. How might you want to turn the 2 logs on the left into 1 log? Yeah.
Can you divide x minus 4 by 2?
There we go. X minus 4 divided by 2. Okay. We have 1 log on the left, 1 log on the right. They're the same exact log because they're both a base 3. So you can imagine those kind of canceling each other out because we already know they're exactly the same. Let's check out the arguments. Where do you want to go from there? Yeah.
Multiply the other side by 2.
Okay, so that would be 2x plus 2. Let's see, a little rearranging. We can subtract the x over, subtract the 2 over. Looks like we get negative 6. All right, so we're going to go ahead and try to check this on the calculator. Now, the little issue with this is the log is a base of 3. So we're going to have to use the change of base formula on our calculator because we only have a base of 10. So if we were to plug in negative 6 into the argument for the first log, that would be negative 6 minus 4, which would be negative 10. So on the calculator, we'll do log of negative 10 divided by log of 3. Okay, that change of base. What happened for that one? No real answer, no real solution. Do you notice how all the other ones we checked, we actually got a number out, but this one isn't? Why do you think that is? Yeah? It doesn't, okay, it's not working. Okay, so somehow log base 3 of negative 10, right, after we plugged in negative 6, this was negative 10, somehow that wasn't able to be solved. But why? Yeah.
Because the x is negative?
Not necessarily this x is negative, it's the argument that's negative, okay? So what's happening here is you cannot have a negative argument for a log. If you think about it, what power can you raise 3 to get negative 10? I mean, you can play around with it on your calculator. We could do 3 to the point 33333. That's still positive. We can do 3 to the negative 2. That's still positive. 3 to the point 0001. That's still positive. Right? You can make this power any number you want. Positive, negative, fraction, anything. You'll never get your answer to be negative. Okay, so the argument of a log can never ever be negative. And that means that this solution we found is actually, we'll say, not correct. Okay, so we'll go ahead and say that this is no solution because it made one of the arguments negative. Actually, if we plugged in negative 6 into the other log we have, wouldn't we get negative 5 for that argument? So it actually makes both of them negative. But if it makes only one of them negative, okay, the entire solution you found, we would have to classify as no solution because there's no way to actually check your work. Okay, so maybe something we'll make note up here at the top. If the equation has no solution, then specify why. Okay, you will always have no solution if the argument is negative. So this is why checking our work, okay, is always important, but especially definitely important for log equations, because you might get a number based off the algebra and the math that we do, but does that number actually work? Okay, you have to check it to make sure. So don't just leave it at face value and think, oh, that has to be it. Okay, we have to check our work. Let's try the last one. Kind of stepping it up here. We have 2 natural logs on the left, 2 natural logs on the right. We eventually want to get 1 log on both sides, so we're going to have to use maybe more than one property here. What do you want to try? Yeah. All right, so on the left-hand side, since we're subtracting, we can divide the arguments. Wonderful. What about the right-hand side? We have 2 logs on that one. We want to get it down to 1. Good, Marie? Yeah?
Can't you multiply 2x minus 1 by 3?
There we go. So we're going to take the argument of 2x minus 1 times the argument of 3. So that would be 6x minus 3. Looks good. 1 log on the left, 1 log on the right. They're exactly the same log, so of course we know they're equal to each other. Let's just focus on the arguments. All right, so kind of similar to the other ones we were doing, we could probably multiply that 2 over. Let's see, we can subtract the x, add the 6. And looks like we get 9 over 11. All right, let's check our answer. Now maybe we can check it without using a calculator, because the only thing we really have to be aware of is if we were to plug this answer back in for x, would it make the argument negative? Okay, that's the only thing we really need to check. So if we were to plug in 9 over 11 plus 3, would that argument still be positive? I think so, right? Because you're taking a positive number and you're adding another positive number, so it's going to stay positive. If we check out the next one, if we plug in 9 over 11 here, we have to multiply it by 2, so that would be 18 over 11, and then we need to subtract 1. That's still going to be positive, because 18 over 11 is bigger than 1, and if you subtract 1, you're still going to be positive. So without even needing a calculator, we can automatically check it in our heads, just to check out to see if it is positive or negative, or whatever the case may be. So we definitely know that this is going to be a good solution. Okay, so moral of the story, properties are extremely important because we have to utilize them to get 1 log on each side of the equation, and we always have to check our work because there might be the case where we have no solution. Okay, if we were to plug in our number back in and we were to get a negative argument, we know that's a no-go. How are we doing? Okay? All right. On Monday, we're going to step these equations up a bit. Okay? We're going to kind of get some difficult ones. Not impossible ones, I'll say that. We'll say difficult ones. Okay?